Test. There we are, back again. Okay. So, okay, we're starting where we left off, where we're doing the calculations for the transformer at the moment in order to be able to select our transformer for this particular design. And I thought I would just draw it up real quick. What we need to select. Basic operation, I'll just put here. Oops. Actually, maybe I will do... Doesn't matter. Or actually, it does matter. Wait. Quasi-resonance flyback converter. That's what we're building, and we already know which type of IC we're going to use. Which type of QR flyback controller, which is this one from Infineon. But we have a bunch of other things that we need to select. Just wanna... Let me try if I can... Okay, yeah, it worked. Make it a bit bigger. Even though I lose a bit of the resolution doing that. Actually, maybe I'll make it smaller again and then rather just zoom in. Which doesn't help. Okay. So this is a simple block diagram of the of a flyback converter, I guess. And what we've already chosen is this part, QR flyback controller. So make that blue. A bit bigger size here. And then we need to select a bridge rectifier. Make that white. And just so we see a little bit which one do we not have yet. So that part. The snubber circuit, we also need to, or this is an RCD clamp. RCD clamp circuit. So this one we already selected. We need this, say, in. And this LP. Now, I talked about it a little bit yesterday with, I think in one of the example schematics, you have this additional winding here, which is a auxiliary winding, which I wasn't familiar with. But basically this part, which is separated, as far as I understand it, in this, and yes, and it can be used to other parts of the circuit, like a 5 volt or something, or even a 3.3 maybe, to power a microcontroller or something, which is really nice. So that's what this is. And maybe that's even what this part here is too, but this, I'm not sure. Diode. And then C out. So that's what we're missing right now. Here I will write transformer. Maybe I should show my screen and not just my face. But there we have it. This is what we have so far. We have the QR flyback controller, which is the IC5QSBG. So that is selected. And of course, the MOSFET here. And I think MOSFET. And I'm not sure if you select that or if this is what is this one again now? Primary capacitor. No. Things we need to find. Or components we need to select. It's basically all of them. Selected component. Undecided. So, just so you see what's going on. We have the bridge rectifier, the in the RCD clamp circuit, the transformer, the diode, the C out. And that's the very, very basic. And then around this component, the controller IC, there's a bunch of other components that are needed too, I'm sure. And then you have the MOSFET down here. Okay, and we're following along this design procedure just to kind of get into it and have some help along the way, because it's can be a bit tedious when you go through this on your own, as I have felt. And I found this article, or this longer design procedure, where it's showing all the calculations that you might need in order to make one of these converters, and also select which transformer, and get familiar with this type of design. I will also, yeah, okay, let's get going. I think last we stopped at choosing maybe the core, and then we ended up here with calculating the primary windings. And there's some things that you need when selecting a transformer, which is the you have to have your initial, current, primary current peak and stuff like this, and also winding ratio in order to get your desired output, and with the defined reflected voltage that you design for. And then there's some things that you don't really need to do yourself, I guess, because you have off-the-shelf transformers that will work based on what you come up with here. The size of the transformer core is determined based upon the output power, P out in watt. The table shows below. Yeah, right. So we said we do the EE25 size, core size, which works up to roughly 30 watt. And this has a core cross-section AE in square millimeters. Okay, so we can move on. I guess maybe I need one of these. Yeah, okay, maybe I need this value 41. So I will write this in cross section to be 41. What was it? Square millimeter. So 41. Core size, output power, we said EE25. Yep. So then we can calculate the primary, wait, I will do like this again. Which is NP E in times T on divided by E times B sat. And this is, since the maximum magnetic flux density B for the commonly available ferrite core is 0.4 TAT or T at 100 degrees Celsius by setting B set 0.35 and substituting into LP and IP peak, we obtain the primary winding turns MP. Here I need to do an additional Google. What is the BSAT in transformer calculations? Saturation flux density of a magnetic core. And do you just select that, or wait? Maybe I need to look into what this material is, the EE25 BSAT. EE25 BSAT. Core saturation. Transformer core saturation. So that the magnetic flux density will fall within the tolerance range, since the maximum magnetic flux density for the commonly available ferrite core is 0.4 Tesla. Is it that? Magnetic flux density unit. Tesla, which is equivalent to 1 Weber per square meter. The Gauss is a non-SI unit where 1 Tesla. All right. At 100 degrees by setting B sat. Okay, so we want the saturation to happen at this point, so it doesn't. Let me just Google max magnetic flux density of a ferrite core. With a common figure being around 400 millitesla for power ferrites. Factors like temperature can lower the usable flux density and core losses, also limit the maximum flux density. Used in designs to prevent excessive heating and core saturation. So the maximum yeah. I'm not entirely sure how they, you know, just decide on that, or if you already got a type of transformer, and then you look at that transformer with a ferrite core, and you know that the maximum magnetic flux density is 0.4 Tesla at 100 degrees Celsius. So by setting it at B, or setting B sat at 0.35, you are below that. My set B sat below the maximum. Yeah, but I guess we can, for now, we'll just use this one, which is 0.35 Tesla. Used from example, investigate the meaning behind this one in particular. No. So then we can calculate this one. V in, which, okay, so we got another step here then. The primary inductance, which you already have calculated, the peak, current peak divided by AE times B set. Which is 192 microhenry times 1.23 ampere divided by 41 square millimeter. So times he said 0.35 Tesla. And that is 192 times 123 16 divided by 41 times 0.35. 1435. So 2, 3, 6, 16 divided by 35. 16.45. Where NP is 20 turns or greater. Yeah, so 17 or greater then, I guess. And here you get the exact. And the next step to prevent occurrence of any magnetic saturation, we set NP from the AL value and I properties. In performing this step, the B set condition formula must be satisfied. Okay, now see if I can understand this. What is it? What is this? AL value 9. Shit. Where did this come from? AL value. AL dash value. An AL value is an inductance factor for magnetic cores, typically ferrite, that represents the core self-inductance per square turn, usually given in nanohenries per turn squared. It simplifies the design of inductors and transformers by allowing engineers to quickly calculate the required number of turns for a desired inductance using the formula L equals AL times N squared divided by 10 to the power of 9. This value is provided by the ferrite coil manufacturer and is specified to the core's size and shape. Okay, so and we wanted core size. I'm not sure which. I think they chose this one, maybe 84, yeah, or one of these, and we do the other one. So if I do EE25 core, ferrite core transformer, and we check just one arbitrary one. I'm just pulling up one random one, and then I wanna see if I can maybe find turn ratio. Yeah, we can also see this auxiliary winding that has an 8-volt output and 20 milliamp rated current, I guess. Here's a 12-volt output, 5-volt, 7.5. Customer terminal. Doesn't really say anything more though. drawing. Wait. What is the AL value of a EE25 farad core? Typical values for an EE25 core made with a common material like PC40 can range around EE25 core. It doesn't say anything. Saturation current, turns ratio. Core shape. Core size. Okay. Okay, here I searched up this one, ferrites and accessories, ER28 core. No. Magnetic characteristics. Here's the cross-section size. Core cross-section, 85 point, no. AL value, 2007. 280 if this that. Inductance factor, which is L divided by inductance factor AL. AL equals the inductance turn squared. And for some reason they assumed or they chose this. And we know the primary. Oh, it's the whole thing squared, not... But yeah, in this case, for example, this type of core, the AL is right here. This type of material, N72 core material. EE25 core. AL value approximate 489. They selected this one, EER28, EE25 core size. Size of E core, ferret cores. Come on now, we don't want to be stuck on this. AL value. Common value is PC47 material. What is that? So, ferret core for switching power supply. EE. E-series. Overview of the E-series. Standard form for use in most commonly used transformers. Shapes are commonly used in Europe. Application switch mode power supply, which is what we're making. This is the material, PC47, size of the core, E25. This one. And here's the AL value. Set is without air gap. Okay. Here's the shape and dimensions. Interesting. I think they showed similar graph. Wait, here. Yeah, value to ni and I limit versus value. Okay, but I need to go to the EE. EE. Core factor. In this case, the effective cross-sectional area AE is 51.8. The AL value is 2000. With the air gap, it's 160. So I'm guessing we want with air gap, huh? So if it's at set, it's without air gap. Okay, let's just look at this one. Low loss switch power. Core factor. Effective cross-sectional area, 40.3. That's similar to what we had there. But this is the 2000 nanohenry. So it's without an air gap, I would guess. Oh, okay, it's the same. What about only that? We take away the set. Okay, let's just calculate it with the 2000. So this type. So the AL value. So we put it in here first. And P is equal to, oh, like this. No. Square root square root. I'm doing it so simple. This was the AL value. Square root of LP 192 divided by 2000. Divided by 2000. Oh. How did I get? So 249. Okay, so 2000. Then the square root of 9.70, 9.8 turns. Ten turns. They rounded up. So let's do the same. So this means if the primary inductance is 249 microhenry, the AL value for 30 turns is 'yeah, then we can put that in here. $192 microhenry divided by 10, which is 2. to 900 turns. Let me just try that. 249 divided by 30 times 30. 249 divided by 900. 0.27. Okay, so so the AL value for 10 turns is 1,920 nanohenry. Which is basically this. And the AL value, what is that again? The AL value, specific inductance is an inductance factor for a magnetic core, like a ferrite or iron powder. Represents its ability to produce self-inductance per square of the number of turns wound around it. Okay. So NE can be determined. I feel like I'm kind of falling out a little bit of the calculations. But we will just continue and see if we were able to pick up. Yeah, NI is equal to that. So we had 10 turns. With 10 turns times 1.23 amps, which is 12.3 amps. Or wait, times turns. Now that A value and NI have been determined from the AL value NI characteristic graph for the EER28 core size, we confirm that the values are within the tolerance range. If they are out of range, we adjust the value of NP. And here they have used this particular ferrite core, I guess. Maybe I can just write that in just to try. AL dash value they limit JFE MB3 just to see what comes up. Yeah. It is for this particular component here. Or ferrite core. For that particular ferrite core. Ferrite core. Yeah. They are made from oxide, made from iron, manganese, and zinc. Calculate the secondary, so we can calculate the secondary winding now. Based on what we have here, secondary winding turns ND. First, we calculate the winding turns necessary to generate the VCC for IC1. Since VCC is 15 volt through the diode D6 on the number of turns, if the VF for the diode is VF VCC, where's the VCC? Do they mean this? The transfer T1 includes a winding ND, oh this one, that generates VCC voltage for the IC1, so for the IC that is controlling. Okay, so since VCC is 15 volts through the diode D6 based on the number of turns D6, but that was the other one. That's D6. That's 12 volts. This is D5. Oh wait, I went a bit too far now. Secondary winding turns. And S. So NP divided by NS was 8, as we saw before. And now that we know the primary, we know that NP is equal to 8 times the NS. So therefore NS needs to be the primary turns divided by 8. We know the primary turns number now, which was 10 divided by 8. Which is 1.25. MP is equal to 1.25. What the hell? So we have 8 turns on the primary, 10 turns on the primary and 1.25 on the secondary. Okay, let's do the last one, which is auxiliary winding, and D. Where ND is equal to NS times VCC times the V, the forward voltage, which was the diode. Oh no, it's the diode on that side. So VCC divided by the V out plus, no, not the, plus V out VD. It's maybe better to use the F, but if the VF for the diode, I will use the same one as before then. Why is VCC 15? Why? Doom, doom. $15 divided by 12. Does that chip take 15 or BD? What was it? BD? But can you select that? Do you select which voltage you get on the auxiliary winding, or? Because that I didn't get. So here you have a diode capacitor into VCC. VCC. Power supply input pin. Power supply voltage range VCC. So this one from 80 to approximately 600. And then here 8.9 to 26. Okay, so VCC is 15. In that case, at least it's 15, but for our yeah, right, here we have it in this block diagram. VCC. Oops. Operating range is between VCC off and VCC LVP. Oops, OVP. VCC is between VCC off and VCC LVP. VCC off and VCC minimum LVP. So here is the threshold. So between 10.5 and 2550. Just want to see on this one if it says anything more about VCC. In this case, it's always yeah. Yeah, 10.5 and 28 was it? 27. A supply, okay, if not otherwise stated, a supply voltage of VCC equals 18 is assumed. Okay, that's what they did here in their calculation, so that's what we're gonna do. Then the windings, in order to get the 18 volts, then is how I read that, is 1.25 times, what did I say? 18. 18 plus 0.5 volts divided by V out, which is 12. plus 0.5 volts. So this is then 1.25 times 18.5 divided by 12.5 times 125. 1.85 turns. Kind of feel like I'm doing something wrong when it comes to the number of turns, but I think maybe because I have a higher high reflected voltage, so effectively more stress on the MOSFET and the higher the number. Because I feel like both of this, if they're not even one turn, is that possible? Or and here, for example, the primary is 34 turns. And here, my primary is 10. I might be wrong. That's okay. We will just go through it. So basically, here, in order to select transformer, we have core, LP, NP, and S, and D. At least we've gone through the calculations once, and then we can go over and check. Okay, we could round it up to 2 at least. Oops. And D to round it up. And here maybe, no. I will Google if it's possible to only have one. Is it possible to only have one winding on the secondary coil of a transformer? No, I suspect that some of like this calculation is somewhat incorrect, maybe. Or maybe it's not that, maybe theoretically it's not, or theoretically it's possible to have only one winding, or in based off of these calculations only have 1.25 windings on the secondary side of the transformer. But practically, like which manufacturer that has that off the shelf, maybe there's a limit. And we get this primary winding, or we get the ratio based off of the reflected voltage. And the reflected voltage, or the flyback voltage, in this case, was selected at 70 volts, so 30 less. And maybe I should even set the duty cycle lower because it's around 0.5 like it says here. It should be set lower than that. We still don't know this one. What is 1.4 and 0.8? But in the end, they ended up on this one. Although the above equations, numerous at a glance, may look intimidating, they are relatively simple formulas. You should try using them. An overall specification have been worked out. You can proceed with a transformer that design task by utilizing the support available from the IC and transformer manufacturers. So TDK Ferrite core transformers. E-cores, planar cores. Oh wow. Okay. But this is just the core. So AC, DC, transformers, master, maybe. Flyback, high efficient resonant converters, maybe. Okay. Power transformers. Secondary voltage, power rating. Okay. Secondary current rating. Okay, I'll take away butch. Flyback transformers. Okay, power rating, we said we wanted it to be 24 watt. So 24 watt and above. Where did the music go? So flyback transformers. Primary voltage rating 85 VAC to 265 VAC. Secondary voltage rating we wanted. We're getting somewhere now. I like it. At least we can select this, select components. Power rating 22. Wait, there was one 25, wasn't it? Oh. That's it. Let's have a look at it though. Secondary current rating, we wanted 2 amps. Can't get that. We can get 900 milliamps. Single primary winding, dual secondary winding. Okay, that leaves us with 1. Oh boy. Power transformer, offline flyback transformer. But it's the inductance isn't right. Here is even the leakage inductance specified. So transformation ratio 8.78 to 1, which is what we had, right? We had 8-ish to 1 or 8 to 1. No. Yeah. Go back to transformers. And then we see if we can get a better one. We want 24 watt. Or let's not limit ourselves to that. Let's not limit ourselves. We need the primary voltage rating. Let's wait. So what we need is we need the right core. Yeah, okay. So just selecting this one, we get 102 possibilities. Secondary voltage rating. $12 and 5 would be good, but maybe we should just focus on only 12. So we get some more options. PCB mount. Let's see what we get here. One of them is 26.4, 2.2. There is also this, oh wait, inductance 681, secondary 14 point, oh that's a leakage inductance. Auxiliary voltage at 16. The ratio. Okay. Now the question really is, can I use this? $249. What was our primary? $192. That doesn't work. Wait, P out. $220. We had 192. One of these were pretty close. This one. So what we need to know is we have the core, primary inductance, primary and secondary windings. Primary, secondary, 12, 22, 26. Yeah, I'm coming back to this one. Like, here the inductance is higher. It has a similar turn ratio, right? And one primary and secondary, which secondary was 1.25, and 3 was 1.85. And inductance 681. Let's go and check which selecting a bobbin. What is this? So this is how it's actually winded together. Number of windings NP1 and then NS1, ND, NS2, and NP2. Whoa. Just skipping through a little bit. Selecting a wire material. And here it's actually down to the MOSFET. But I don't think they mentioned which transformer they chose. Selecting transformer for a SMPS or AC/DC flyback converter. Maybe I'm making it a little bit too complicated. Calculate the peak primary current and primary winding inductance. No, I mean you need those calculations. You need to know the primary inductance. You need to know which core in order to handle the output power. You need to know the relationship here with the primary windings in order to, and then the secondary windings in order to get the correct output voltage. And all of that we get here, right? Maybe some of these you can maybe skip a little bit, I don't know. No, I don't think so, because here you use, even for the number of primary windings, you use the cross core area, cross section, and the magnetic flux density and maximum magnetic flux density. Core size, consider mechanical and practical aspects. Selecting a bobbin, like here, in order to have enough pins for the windings, all primaries and all secondaries. Selection guide, okay. Cool. So power rating 24. Output 12 volts, 2 ampere. Nominal frequency, primary to secondary 1 to 0.5. Turn ratio. Maybe that doesn't work. Or what did we say? The primary is 10. Secondary was 0.25. Right. Wide input VDC. Yeah, okay. Let's go a bit further down here just to see. 10 divided by 1.25 was 8. Yeah. 1 to 10. 1 on the primary, 10 on the secondary. Okay. This one I will save. I think we should be able to. I should be able to select some or one of these. L at 0 amps. Microhenry. We had 192. So maybe the 200 one here. It looked promising in the beginning with this one. Okay, but that's it for today. I need to continue another day. Thank you for watching. This one I will also save core and bobbin selection for the transformer. Okay. Some progress was made, so that's fine. Okay, peace.